And we are back. So let's see, where we left off, we were talking about limit cycles. And now what we're going to do is start to figure out when they exist, and more importantly now for the next few sections, when they don't exist. So what we're going to do from our outline in the previous section, we're going to figure out what ways we can rule out limit cycles within autonomous systems. So one of these ways to rule out limit cycles is to establish that the system that you're looking at is gradient. And what that means is that there is a potential function for this system, right? This is not the same thing as being a conservative system, right? That one we're looking for an energy function. This one we're just looking for a potential. Okay, so usually conservative systems you think of as coming from, coming from a second order ODE. So usually this is going to be like a conserved quantity is going to be based on like mechanical energy or possibly angular momentum, something that is related to classical physics or classical mechanics. In this case, the gradient, we're going to see it exactly as we did in one-dimensional systems, right? So we're just asking for the function f to be a force resulting from a potential field v. So what we can say is if the system can be established as being gradient, then there's absolutely no way for there to be a closed orbit solution anywhere. So not just no limit cycles, but no periodic orbits whatsoever, no periodic solutions. So the proof of this theorem is actually strikingly similar to what we looked at in first one-dimensional systems. So we're going to go ahead and outline that proof for the higher dimension, for higher dimensions in general, so not just for 2D. This applies for any dimension. And a similar argument actually works for arbitrary Riemannian manifolds, where we can use different inner products, something other than dot product on Euclidean space. So in order to figure this out, in order to show how we don't have any closed orbit solutions, we're going to go ahead and pick an initial condition, or pick a starting point for this orbit. So suppose that we do have a closed orbit, right? And we're going to parameterize that guy as a solution x of t. And we're going to say that after a time capital T, right, this positive period, we're going to go ahead and say that this guy closes up. Now, this could be any number of values, but we're going to make sure that this is the smallest value, positive value t, where this cycle closes up, right? Because we could go to 2t, 3t, 50t, 5 billion t, any integer multiple of capital T. We just want to make sure we have one circuit. We want to go around the loop once. So if we do that, notice that the potential function, if we're dealing with a gradient system, the potential function will evaluate to the same value, x0, or at x0, which would be the same as looking at going around this loop, starting at little t equals 0 and going out to little t equals big T. So that would be that we would be able to use the fundamental theorem of line integrals on a closed path to say that the circulation of the gradient of v is actually equal to what happens when we parameterize, right? So the circulation would be this term here, right? So we're saying that circulation, because this is a gradient, we can go ahead and write this in terms of a net difference of an antiderivative. But we are going to go the opposite direction here and parameterize this curve, so dropping down to the next line, we are going to parameterize our orbit with the solution little x of t, which means that our dr vector is going to separate as a velocity times a small chunk of time, so dx dt times dt through a chain rule, which would in turn allow us, since this velocity term is exactly equal to, the other one, not the velocity term, the potential here, right? The gradient of the potential, this is exactly the definition of the system, right? If it's gradient, then x dot is equal to the negative gradient of v. So throw the negative sign onto the other side of the equation, so grad v is actually equal to the negative velocity, the opposite velocity of the trajectory. Now, dot product of any vector with itself is going to be the length of that vector squared, and we picked up a minus sign along the way. So that means that we're integrating a non-positive function, and in fact, the only time, because this is a Euclidean dot product, the only way that we are going to hit 0 inside here, right? The only time that this guy is going to be 0 is if x dot is 0 itself, which would correspond to a fixed point. So the only way that we're going to make this this inequality into an equality, the only time this guy would be 0, is if we were sitting on a fixed point for the entire length of time from 0 to capital T. Since we're assuming we're on a closed orbit, and for a fixed point, these are periodic solutions that have effectively 0 period, right? Or you just say they're not periodic solutions at all. So in order for us to have a positive capital T, we can't be sitting on a fixed point. So that means that this inequality is actually just a strict equality. Therefore, this inequality in equation star is strict. So we came to a contradiction here that 0 is actually strictly less than 0. So the only thing that was wrong with the argument was the assumption that we had a periodic orbit, or a periodic solution that wasn't a fixed point. Therefore, that can't exist. So there are no limit cycles, there are no closed orbits for gradient systems. It just can't happen. And there would be a lot of information to there's a lot of different ways we can go from here, a lot of different directions we can take this. So let's go ahead and narrow the scope a little bit. So we've established gradient systems have no closed orbits. So the question then is, how do you determine if a system is gradient or not? So there is a quick check to determine specifically if a system is not gradient, right? This one is actually very straightforward, and it's a quick check that you should remember from vector calc, or multivariable calc at the very least. So suppose that we had some arbitrary system, right? That would be this guy on the left, right? Suppose we have that system, we have an arbitrary vector field f by g, and this is planar, just for the sake of argument. Yeah, most of the time we're dealing with these two-dimensional systems, so it suffices for right now. There are other conditions that we can check for higher dimensional systems, but let's go ahead and stick with 2 dimensions for right now. So if we do have a gradient system, right? So if x dot is equal to a negative gradient of a potential, then the function v would have to satisfy the following 2 conditions on the vector field f by g, right? If our vector field has to equal a negative gradient, then v has to satisfy a pair of differential equations. In fact, a pair of PDEs, right? It's a simultaneous pair, so this is a system of PDEs. So if the potential does indeed satisfy these equations, so let's say, forget actually solving this for right now, let's just say that v did solve it, right? And it has to if it's a gradient system. Then we can go ahead and differentiate this first equation with respect to y. And then we can differentiate this second guy with respect to x. Now, why would we want to do that? Well, it boils down to these 2 terms on the left. Differentiating partial v partial x with respect to y gives me the yx, or the y after x partial. So this would be v sub xy on top. And then on the bottom, I would get x after y. So I would have two second-order partial derivatives of v, which would have to be the same if my potential function is nice enough. And this is exactly what we're invoking in the next couple lines. We're going to go ahead and say, that if v satisfies the system of PDEs, then that would mean that, let's do this back in red, that these two functions on the stars here, like the two ends here, they would have to be the same. So if I belong to a gradient system, then the vector field actually has to satisfy this condition on its partial derivatives. So that is to say that if I don't get this inequality between partial f partial y and partial f partial g partial x, then there's no way that I could be a gradient field because I couldn't get this equality in the middle on the mixed partial derivatives. Right? So this is exactly what the theorem is saying below, or the proposition I suppose. This proposition says the converse, contrapositive. If these two derivatives, right, if I bring the system up so you can see it up here, there's my vector field on the top, f by g. If the y partial of the first component, f, is not equal to the x partial derivative of the second component, then that planar system cannot be gradient, because I would miss out on the mixed partial derivatives being equal. And we can see this in the following example. This guy, this system down here, right, this guy. This is clearly not going to be a gradient system. We actually know what this looks like. This is our prototype circulation vector field, right? So notice the condition from the proposition. If I differentiate that first equation, the f of x and y equals y, if I differentiate that with respect to y, then this is not the same thing as the -1 that I would get from differentiating g, which is this minus x equation, or minus x expression, with respect to x. So there's no way that that this vector field is gradient, right? Which means we could rule out closed orbits here if it was gradient, but in this case, you can actually see, if we have closed orbits, then the system is clearly not gradient. And this is exactly what this guy looks like. If I bring him down here, this is the phase portrait, or a phase portrait of this system. Right? I have closed orbits, therefore I can't be gradient. All right. So that's kind of seeing this proposition in action. I'm just trying to show if these guys are not, if they don't satisfy a particular relationship, then the system is not gradient. But we want to also know, is the converse of the original statement we were talking about up here. Yeah. So if I'm gradient, then I have to satisfy, the converse. So that would be this statement here. If x dot equals minus grad v, then f sub y has to equal g sub x. The question now is if the converse holds. So specifically, if I can establish that the relationship f sub y equals g sub x does hold, then is the system gradient? It's actually a really, really sensitive topic here, a really sensitive statement. But yes, it is gradient, but you do have to be very careful about what kinds of closed loop integrals you're allowed to say are zero. Specifically, we're going to have a statement saying that the path integrals are not necessarily path independent. Right? And we'll show an example of what this means exactly. Right? So the theorem that we're going for here is the converse. We're saying that if we are a planar system over some connected open set, oh shoot, no, that statement is wrong. I'm looking at this little bit down here saying there is a potential function for the system. Yeah, so this statement is perfectly fine. Let me see if I can't fix it on the fly here for the system. Let's kill that off and space it out. Bring it down. Then there is a potential function and the closed loop integral here of f dot dr over c is 0 for all curves, all simple closed curves. Curves in D. If D is not simply connected, oh no, okay, I didn't say simply connected, I just said connected. Okay, then this guy is perfectly fine. Okay, he was perfectly fine the way I had him. Okay, let's see if we can't back that up. Back. And actually, it's probably easier just to start erasing instead of undoing. There we go. Yep. And we can get rid of that. Oh, we'll bring the H and the O back. There we go. And insert space. We're now going to close that space. I love this program. Okay. So for the system, right. I'm not saying right here, I didn't say not simply connected, right? And that was the thing that was bothering me. Because if that domain D was simply connected, then yeah, sure, this is great. That's probably the best case scenario we could hope for. But I didn't say simply connected, which means that I have to be careful about that open connected set. Right? This D is a problem child here, right? Our system can be gradient, no problem. But there is an issue with taking path integrals by integrating over closed curves. In fact, just anything, not even a closed curve. Our path integrals, our line integrals, or work integrals are quite possibly going to be path dependent. And I'd like to go through an example here saying what the issue is. So bottom line, if you satisfy this this condition in the partial derivatives on your vector field f by g, then you're fine, right? You will definitely get a gradient system. The problem is the domain, right? Figuring out where you would like to operate. Okay, so let me demonstrate what that means, or what the key issue is. But first, let's say we're in this nice scenario where we do in fact get a gradient field off of this. So by example, we're just kind of demonstrating. So it's not really a proof, it's more of a quote-unquote proof. Right, so we're just giving a proof of concept, really, to show you how this works. And I'm just reminding you, you should remember a good portion of this from Calc 3, so multivariable calc, or vector calculus if you've taken it. This method is outlined in there. So let's go ahead and start with our system, this arbitrarily chosen one, or maybe I crafted it to be nice and pretty. So let's go ahead and have a look. So this system, oh geez, work with me. There you go. This system up here, I chose it very specifically, right? I cheated. I chose the potential function and then created the vector field, but shh, don't tell anyone. We are going to go ahead and start with the vector field and try to reconstruct the potential field. So let's go ahead and say that grad V is negative f. So in other words, say we were sitting in some gradient vector field. Then v sub x would have to be the top equation, or the top right-hand side, and then v sub y would have to be the bottom right-hand side with the negative sign thrown in there. Right, so notice we had a negative sign and then a plus up here. Now it's plus minus. Okay, so do be careful. Anyway, there we go. So let's see if we can't get back up to v. We know what v sub x looks like. We know what v sub y looks like. Pick one of them and integrate. We're going to do partial integration to figure out what the general form of this guy looks like. So if I integrated with respect to x, so I started with, let's go ahead and label this guy equation 1. If I started with equation 1 and integrated with respect to x, I'm going to wind up with, well, x squared y squared plus e to the minus x. And then it's not an arbitrary constant of integration anymore that we have to add, so not quite this plus c, because there are other variables in town. Right, if I differentiate an arbitrary function big G of y with respect to x, then it goes away just like an integration constant. So instead of just saying plus c, we have to tack on an arbitrary function of y. And very, very similarly, if we were to start with, let's label this guy equation 2, equation 2 integrates with respect to y to get back up to v. So we still get that x squared y squared bit, but we also get a minus sign of y plus an arbitrary function that is an h, not a pound, or not a hashtag. So we would have to add an arbitrary function of x into this integration. Okay, so either way works. Either direction you want to go with it, it's perfectly valid. So let's have a look. If partial v partial y, right, or maybe if partial, no, we're going to go ahead and start with this guy. We're going to say, let's take v, and this came from the x equation, so we're going to differentiate it now with respect to the other variable. We're going to differentiate it with respect to y. If I do that, I'm going to wind up differentiating that entire v function itself, but then I have to set it equal to whatever the g function was in the original equation. It's this guy up here, or at least his opposite, so maybe it's the right-hand side of equation 2. So after setting these two guys equal to each other, I see that g prime has to be exactly equal to minus cosine of y, which means that g itself would have to be minus sine of y, and then I get an arbitrary constant of integration, because I've already taken care of the fact that this is not a multivariable function anymore. G is only a function of y. V was a function of x and y, but g is just a function of y, so I can integrate just like in Calc 2. No problem. Okay, so I'm able to completely solve for the entire family of functions. Right, this would be the original v, and then g is this tail end here, g of y. I would be able to solve for any one of these guys. Any choice of constant c is going to give me a potential function for this system. But now, that's the method that we should remember from multivariable calc. On the other hand now, let's say that I did have a gradient system, so I did have a potential function, and I had a system that was, what would it be? So the system associated with this would be, yeah, so it would be x dot is equal to, let's see, y over x squared plus y squared is minus x over x squared plus y squared. Right, so I'm just saying, here is my new system, and I've designed it so that it is a gradient system. And, well, the problem here isn't in the fact that I've been able to construct a gradient off of this, right, or that I've been able to construct a potential function. It's in how I apply that gradient field. And the problem lies right here at the origin, where I'm not allowed to divide by 0. So the thing that's going on here, let's see what happens if I try to integrate from -1 to 1, but by taking different paths around the origin. And I think we can look at this very quickly and see that the top path here is moving against the vector field, whereas the bottom path is moving with the vector field. So automatically you're going to see that one of these, the top path, is going to integrate, the work integral is going to integrate to a negative number, but the bottom path will integrate to a positive number. So that means that this is not this integral, this work integral of f dot dr, that this guy is path dependent. Right, it depends on how I go from one point to another through this vector field. And it's the problem here is not that this is a gradient field. but rather that this is not a conservative vector field over any domain that contains the origin. So it's the domain that I'm integrating over that's the problem. Okay, so I actually include all the work down here. So if you want to compute this out by yourself, I'm not going to make this the focus of the exercise. I'm just showing you that it's not, like, you can be a gradient system, but you do have to be very careful about the domain that you're using, that D set, to make sure that it is that the vector field is conservative over that set, where all the work integrals are path independent. Phew. Okay, so bottom line, it is perfectly fine for us, right? I'm down here at the bottom. The moral of the story is that this condition f sub y equals g sub x is enough to show that this system is gradient. But we do have to be careful about any line integrals that we want to compute, because the domain that we use might actually make it so that the vector field f by g is not conservative. So any line integrals might actually be path dependent. So we do have to be very careful, right? That'll conclude the gradient section, or showing that gradient systems rule out closed orbits. But again, we do have to be careful. So I will see you in the next section. We're going to start looking at a different version of gradient systems. So something that is near gradient, but actually dissipates energy a little more generally.